In this video, I want to take a look at the geometry of matrix transformations when the matrix is invertible. In the previous video, we looked at this graph and watched how the unit square got transformed. And we saw several things. For instance, if I use this matrix here, B is the transformation that reflects over the line y equals x. And if I did, this is reflection across the y-axis. This is reflection across the x-axis. This would be reflection across the x-axis and an expansion in the y direction. And this last one over here, D, is a shear. One thing to notice about all of those matrices that I just looked at and the transformations corresponding to them, these matrices are elementary matrices. And it turns out that we can say precisely what the transformation is when you're multiplying by an elementary matrix. So here's the theorem. The theorem says if E is an elementary matrix, a 2 by 2 elementary matrix, so the transformation T sub E from R2 to R2 is one of the following. It's either a shear, or it's a reflection all across y equals x, or it's a compression, or it's an expansion. Those two I think are the same, right? Either expansion in the x direction or in the y direction. Or it's a reflection about one of the coordinate axes, or it's a combination of a compression, an expansion, and a reflection, right? That's when we're multiplying one row by a negative number. Now, that allows us to say the following. If TA from R2 to R2 is multiplication by an invertible matrix A, then the geometric effect of TA is the same as an appropriate succession of shears, compressions, expansions, and reflections. And the way that we show that is we say, hey, if A is invertible, A can be written as a product of elementary matrices. And then you look at that product. You got a whole bunch of matrices all multiplied together. The first one, oh, that's a reflection. Oh, the next one, that's a shear. Oh, the next one. And so you just write it as a product of elementary matrices, and you say what those things are, what those transformations are. So let's do one example of that. So here's my matrix A, 1, 2, 3, 4. What I want to do is I want to figure out the transformation T sub A. What is it? Is it reflections? Is it rotations? Is it what? Well, here's what I'm going to do. I'm going to try to write A as a product of elementary matrices. Now, first of all, I noticed that it is invertible because the determinant is 4 minus 6, negative 2, which is not 0. So it is invertible. And so what I'm going to do is I'm going to do a sequence of row operations to get it down to the identity matrix. And I'm going to pay attention to what I'm doing each time. So the first thing I want to do is I'm going to replace row 2 by row 2 minus 3 times row 1. Okay? And there's the elementary matrix that would do that, right? So if I started with the identity and did the same thing to the identity that I just did to A, that's multiplying the top row by negative 3 and adding it to row 2. Then multiplying A by that matrix on the left is the same thing as doing that row operation. Likewise, what I did next, maybe this is sort of a non-standard thing to do, but I just added row 2 to row 1. So that matrix is right here. And so again, so there's 2 row operations. A has been multiplied by 2 elementary matrices. And then the last thing I need to do here is multiply row 2 by negative a half in order to turn that into 1. So there's the elementary matrix that does that. Now, at this stage, I don't have A written as a product of elementary matrices. I have I written as a product of elementary matrices times A. So what I need to do now is solve for A. So I'm going to multiply on the left by the inverse of this thing. So that ends up here. And then I multiply on the left by the inverse of this thing, which ends up here. And then the inverse of this one, which is here. And these inverses are reasonably easy to calculate because the inverse of subtracting 3 times row 1 from row 2 is adding 3 times row 1 to row 2. So there's that. Likewise here, that's just a minus 1. And the inverse of multiplying by negative a half is multiplying by negative 2. So here's A now written as a product of elementary matrices. And now I can say what A is. And I'm going to read from right to left, because if I multiply A times the vector x, then the x would go over here on the right. So the first thing that gets applied to it is this matrix. Right? So the first thing that happens here is this is an expansion in the y direction by a factor of 2, followed immediately by a reflection across the x-axis. Or you could think of it as an expansion by a factor of negative 2 in the y direction. Then comes this, which is a shear in the x direction by a factor of minus 1, and then follow that by a shear in the y direction by a factor of 3. And that supposedly is the geometry of what's happening here. So let's take a look at that. So here I have the vector 1, 2, 3, 4, and the unit square here is being moved up to, if I animate this here, it should go up to there. And it looks like it flips over as it goes. And so the question is that the same as the product of those 3 elementary matrices? So I have them here, this one, that one. So what I wanted here, let's do D first. So let's take this, put a D in there. So there's the expansion in the y direction by a factor of negative 2. So, right, the unit square gets pushed down to there. I'm then going to shear in the direction of x with a factor of minus 1. So there's the C. So out in front of the D here, I want to say times C. Now, notice I said minus 1, and yet it looked like it pushed this thing to the right. Well, that's because you're looking at on the negative values of y. On the top side, it would have pushed it backwards minus 1. But this is being pushed forward because y is negative. So it's negatives times negative 1. Okay. So there's that shear. And then I need to multiply out in front of that with matrix B. And sure enough, it gets me up to the same thing. A couple of things to notice here. I suppose it'll come up at some point in the text, but I haven't seen it yet. I want to point it out, though. The determinant of this matrix was negative 2. And it flipped over, right? It took the unit square and it flipped it over. It turns out if the determinant is negative, the transformation is going to flip the unit square over. Also, the absolute value of the determinant is the area that the unit square ends up. So this parallelogram, this big parallelogram up there, has area 2. Anyway, there you go. There's some geometry of transformations of invertible matrices.